Hello world, Joshua here at JTC Education, and today we're going to be talking about the physics of music. It's one of my favourite topics in the world. Unfortunately, we're only going to have time to scrape the tip of the iceberg, but nevertheless, I hope you will enjoy. Okay, so to talk about the physics of music, we need to talk about waves. In particular, we're going to talk about two types of waves, which are progressive waves and standing waves. In reality, waves split into many categories: mechanical, electromagnetic, transverse, longitudinal, the list goes on. But for the purposes of this video, we're just going to talk about two types of waves. So what's a progressive wave? Well, a progressive wave is a wave that goes from one point in space A to another point in space B, and it transfers energy from that point to the other point. For example, if I have a speaker, the speaker vibrates, it causes a sound wave by compression and rarefaction of the air, and that sound wave travels across the air to our ear. This would be an example of a progressive wave. However, if I looked at a guitar and I plucked its string, sure, I can get a wave on the string. It might go up and down like this, or it might look something like this. But what I can guarantee you is that wave is not going to be traveling anywhere overall. It is between two fixed ends, and therefore it is a standing wave. Now, it's important that we understand this because inside the instruments, be it guitar, be it fife, be it saxophone, we have standing waves. Okay, when I pluck a guitar string, I create a standing wave. But that standing wave is what causes compressions, high pressure, and rarefactions, low pressure of the air. And in turn, those compressions and rarefactions of the air cause a progressive wave, which takes the beautiful and wonderful music right to our ears. Okie dokie, so let's have a talk about guitars. Now, we've established that the strings at each end cannot move. So when I'm drawing the waves that can fit on the guitar string, I must always start here and end here. And therefore, the first wave that can fit in is simply this wave like this. Just so we're clear, this is the same as this wave down here. They're the same thing. They're going to go up and down like this. This is the first wave that can fit into the guitar. The second wave that can fit into the guitar is going to look something like this. It's going to go up, down, up. Okay? It still satisfies the criteria that at each end of the string it is at the equilibrium position, as it must be because it's fixed in place. And the third wave that fits in will look something like this. 1, 2, 3. Okay, they're the first three waves that will fit on my guitar string. In a second, I'll play them on the guitar. Let's have a little look at some of the maths to do with these waves. Well, first of all, let's examine this wave here. First of all, we need to remind ourselves of V equals F lambda. Yes, speed equals frequency times wavelength. It's called the wave equation. If you're doing GCSE physics or A-level physics, you should absolutely know this equation. I'm going to call the length of the guitar string L. So how much of this blue wave is on the guitar string? Well, just half a wavelength. Yeah, the full wavelength would be off down here. So I can say half a wavelength, lambda over 2, equals L for this first blue wave here, which gives me lambda equals 2L. And I can then use that in my V equals F lambda. I can rearrange to make F the subject, so F equals V over lambda. I can substitute in this that I've just found, lambda equals 2L, so I get V over 2L, and bingo, I have an expression in terms of V, this wave speed, and L, the length of the string, for the very first frequency that will fit into this guitar. And I can do an exactly analogous thing for the next string, the next wave that fits in. So in this case, this orange wave, this is one whole wavelength. So for the orange wave, wavelength lambda is L. Okay, and I can simply say F equals V over lambda. We've established that before. That's just rearranging this equation. So it's basically V over L. And this is really interesting. This is 2 times this, right? If I times this by 2, cancel, cancel, I get V over L. So I can write this second frequency as 2 times the first one. And now I'll just do it for the purple one really quickly. It's going to be exactly the same drill again. So I need to look at this wave. There is 1.5 wavelengths that fit onto the guitar string here. 1.5, 3 for 2 wavelengths of a length of the guitar string. If I make lambda the subject of this, I get 2 over 3L, and if I sub it in my F equals V over lambda, remember that came from here, I get V over 2L over 3, and if you know how to deal with your fractions, when I divide this fraction I will get 3V over 2L. And that's interesting, that is 3 times this one over here. So I can write this as 3 times F1. Now, we can probably spot the pattern that's going on here. We can see that the first frequency has V over 2L, the second frequency is 2 times the first, and the third frequency that fits into the guitar is 3 times the first. And these are what we call our harmonics. Harmonics are what multiple of the fundamental frequency is the wave. This is 2 times the fundamental, therefore it is the second harmonic. This is 3 times the fundamental, so it is the third harmonic. And on the guitar, I can excite all the harmonics. I can do 1, 2, 3, 4, 5, 6, etc., all the way up. Let me just show you exactly how this works. So my first harmonic would be just me plucking the string normally. Okay, I've excited this blue wave here. Okay, the first one. Now, if I hold my finger down very gently in the middle of the string, I can create what we call a node here. That's the point of zero displacement, this little point in here. And I should be able to create a wave that is double the frequency. Now, double the frequency in music is 1 octave. So I'm going to hold it down very gently here. I'm going to create a node, i.e. a point that can't move. And bingo, I get a second harmonic. And if I am really good, I can cut it off exactly a third of the way, and I can create the third harmonic. So I need to cut it off here this time. Let's have a look. Actually, the 7th fret on the guitar is exactly a third of the way. There it is. There's the third harmonic. Now, if I weren't exactly a third of the way, I just get a dud note because the wave can't fit in. Exactly half of the way. Perfect. Second harmonic. Third harmonic. And if I can go a quarter of the way, it's a bit more tricky. Missed it there. There it is. The 4th harmonic. 4 times the fundamental frequency. So, at this point, you might quite justifiably be asking yourself what the difference is between me holding the string very, very lightly, so not actually pushing it down and exciting a harmonic as such, and actually fully pushing the string down. And there's quite a significant difference. When I'm holding it down lightly, remember I'm exciting a harmonic, so the whole string is still in play. The only thing that matters is a wave can still fit onto that string. So I must either hold it a third of the way, a quarter of the way, a half of the way, etc. If it's not an integer division of the string, then this wave can't fit in. Indeed, that's why if I go here, nothing, because this wasn't a third, wasn't a half, it wasn't an integer division of the string. On the other hand, if I actually hold the fret down, I am simply shortening the length of the string. So this is the first harmonic, it's just on a shorter string, which goes from here to the bass now. And I can shorten the string to any length I wish. There it is, shorter again. I make it shorter again, and we can see as that length is decreasing, the pitch, i.e. the frequency, is getting higher. And that's very easy to explain from the equations before. If I look down here, I saw that my frequency equals V over 2L. In other words, my frequency, if my V is constant, is inversely proportional to length. And therefore, indeed, as I go up the frets and my length gets shorter and shorter and shorter, my frequency and my pitch gets higher. Cool, so now we can talk about the physics of the fife. And actually, the physics of the fife is very similar to the physics of the guitar string. The only difference I would say is that on the guitar, it's fairly obvious that the ends are fixed. You can see that the string can't move. It's a little bit less obvious how this works on the fife, but essentially there is a sound wave in the fife, and because both ends are open, we can be certain that it's always in equilibrium with air pressure. So out here I have air pressure. Inside the fife, I have the pressure in the fife, which is going to be going up and down in compressions and rarefactions as a sound wave travels down it. But at this end here, the important thing is that it has to be balanced with air pressure. I can't have this sudden jump from a high pressure in the fife to a low pressure outside. It just doesn't make sense. Pressure is continuous. So effectively, I can say that if this marks air pressure, I can say that it's always got to be fixed at air pressure here, P air, and also over here because this is also an open end. And then once again, I can simply draw in the waves that will fit. So the first wave that will fit is just like in the guitar. like this. The second pressure wave that will fit in will look like something like this, right? They're exactly analogous to the guitar. Indeed, if I cover up all the holes, this is something I should have mentioned before, if I'm covering up all the holes, this is the first open end. And if I cover up all the holes, I will get these waves. And I can excite the second harmonic. I just need to change how I shape my lips. And it's 1 octave higher. And if I were a better 5 player, I could perhaps get the third harmonic. There you go, almost. On a good day, sometimes it comes out. So what happens if I start to take off fingers on the 5? Well, if I take off a finger, the same thing happens as if I shorten the length of my guitar string. So let me move the 5 out of the way. Let me shorten these waves. And you can see, effectively, the open end is now here. And therefore, the wave ends at this point. Therefore, the wave is shorter, the frequency is higher. This is exactly like shortening the length of the string. Great, so finally I promised that we would talk about an instrument in which you can't get all of the harmonics easily, and these are instruments such as the saxophone and the clarinet. Now the interesting thing here is this is an open end, so as previously agreed, this will maintain at air pressure, it will stay at this pressure no matter what. But this end here is closed, right, because I'm going to put my mouth over this end, and therefore the air pressure can go from a maximum to a minimum because it doesn't have to stay in equilibrium with the air outside. Indeed, my mouth is a boundary effectively, and the air particles can group up and space out, so I can go from max to min. Now this is really interesting because this means that the first wave that I can draw in here this time looks something like this. Let me draw this on a little bit of a smaller scale. It goes from max to middle. This is a quarter of a wavelength. Remember, a whole wavelength would be continuing down here and all the way back up here. So this is just 1/4 of that, right? This is 1/4, 1/2, 3/4 and a whole. Sorry, I haven't drawn it very well to scale there. So I can do the whole mathematical analysis again, but with waves like this. The second wave that will fit in will go up here, down, and then it has to come back to the midpoint. Let me just draw the middle line here for clarity. The next wave that will fit in, I'll change the color of my pen, will start here, it will go down, up, back to the midpoint. Let's just do this first wave that I drew here. So I've agreed that basically 1/4 of the wavelength is the length of the saxophone, which means that lambda equals 4L, and remember we established that F equals V over lambda, so in this case F equals V over 4L. Remember before, if I flick back, it was V over 2L. So for starters, that's interesting. That tells me that I'm probably going to get a lower note on my saxophone for the same length compared to my fife, which was the same as the guitar. And the next interesting thing to note is let's look at this second wave. So the second wave, let me just go over it in yellow for clarity. This is the second wave that fits in. It starts up the top, goes down, and then it has to come back to equilibrium air pressure. Well, that is 3/4 of a wavelength, right? Half down to here, plus an extra quarter of a wavelength. So 3/4 of a wavelength equals L. That means that lambda equals 4L over 3. F equals V over lambda. We've just established lambda is 4L over 3, so V over 4L over 3, which is 3V over 4L. This is super interesting. This is the next wave that fits into the saxophone, and oh my gosh, it is not just 2 times this. It is actually 3 times this. This is crazy. This is crazy. We have our first harmonic, and we cannot get a second harmonic out of the saxophone. We actually can only get the third harmonic, 3 times the first one. And that is why on the saxophone, unlike on the fife, there is this special button here which will open this end of the saxophone. What does that do? Well, if I open the ends, it's like having an open hole, and I must once again be in equilibrium with air pressure. It is indeed this that allows me to get that second harmonic that looks like this, because I can be back in equilibrium with air pressure. I don't need that on the fife, because it's open end, open end. Open end here, open end here. I get the exact same waves as I did on the guitar string. But with the saxophone, I don't have a choice. I've put my mouth over it, so I've blocked it off this end, so I definitely have what we call an antinode, max, min, pressure over here. I am definitely in equilibrium with air pressure. The only way in which I can get a second harmonic is by using this button here. Other than that, the mechanics of the saxophone are all the same. Let's give it a little go. This is my soprano saxophone, so it's a little bit more tricky to play. Let me just tighten up the strap. Okay. And now we can see if I play the same note again, but this time I open up this little hole here, the air at this end of the saxophone will be held in equilibrium with the air pressure, and therefore I'll have an open end. I'll be able to excite the second harmonic just like I did in the fife, and that will be the octave. Let's give it a go. And so finally, using the keys to change the length of the wave in the saxophone and hence the frequency of the wave, and this little button up here to reach the octave, I can jam out to some John Coltrane. And there we have it, the physics of music.